First, we're going to the introduction, then looking at the experiments, and then conclusion with final conclusions. Purpose of this lab is to capture the motion of an object that is thrown and moves like a projectile. This will be accomplished by comparing a real-world experiment to a perfect computational model. This lab will also observe the effects of no drag force or air resistance and compare it to when drag force and air resistance are present. A couple of assumptions that we make is that only forces acting on the ball are gravitational and drag forces, and we can assume all projectile concepts as an example of projectile motion. Some fundamental physics principles are Newton's second law: an object in motion will stay in motion unless influenced by an outside force. This formula is just net force equals mass times acceleration, and it's equivalent to momentum principle. And using the definition of these variables, we can derive both a velocity and position update equation. So Newton's second law is just F equals ma. Momentum principle, the change in momentum equals the net force times change in time. And this is the position and velocity update equation, and then we introduce the drag force equation in this lab. Other fundamental principles, some of the other fundamental principles include drag force and force of gravity. And so the acceleration of gravity near Earth's surface is just negative 9.8 meters per second squared. And it's represented in vector form as g equals 0, negative 9.80. And the force of gravity is just equal to 0, negative mg, 0 newtons. And it's always in the minus y direction due to its attractive nature and properties. It is directly proportional to the object's mass in every situation. Drag force acts directly against the motion of the object, and in this scenario it is the air acting against the motion, or the object while it's in motion. Direction proportional to the surface of the area of the object, and the b in the equation is a proportionality constant that's determined in the experiment. For this experiment, a metal ball wrapped in paper is thrown in front of a whiteboard. The system is the ball wrapped in paper, and the surroundings are the whiteboard, the room, the air, and everything else in the room. Mass is the mass of the paper ball and our metal ball wrapped in paper is 0.012419 kilograms. The initial velocity was calculated to be 1.281 meters per second in the x direction and 3.485 meters in the y direction, and it took about 2/3 of a second. And the initial position is started at 0.533 meters in the x direction and 1.09 meters in the y direction. And there's a calculation for initial velocity. For the procedure, we videoed the motion of the ball, we uploaded the video in a tracker, we copy and pasted the starter code in the Glow script to run the computational models, and we compared the results. So this is what it looked like in tracker. So you can see we tracked the ball as it's going through the motion, and we got this data from tracker. And so as we can see, we have a straight constant line for the x direction. And for the y direction, you can see we have the projectile going up, and then once it reaches its peak, it goes right back down. And for the no drag computational model, we enter the mass and then the initial position and velocity, and we start at time equals 0, and delta t is 0.033 seconds, which is for each frame, and the force of gravity, or the acceleration of gravity, is 9.8, and since we're not accounting for drag force, b equals 0 in this scenario. And F net is just equal to Fg, because which is just negative mass of the ball times gravity, and then Fd we can ignore because we're not using drag in this scenario. And then we have the velocity update and the position update. And then with drag, the only thing that changes is our calculated b value is about 0.001, so we include that. And now the F net is force of gravity plus the force of drag, which we're given by this equation, or which we get by this equation. And for the results, we can see this is our data, and so we can see that as that it's not perfect, but we can see that the computational model with drag is a little closer than the one without drag. And so overall, all the models show a similar trend. However, we can see that the model with drag is more realistic than the model that doesn't take drag into account. The model with no drag goes a little higher and takes a little longer to come back down versus the model that does actually factor in drag. So possible source of error is human error, tracker positioning. So for example, human error because when you position the tracker, you could hit different points of the ball. An imperfect trajectory because we don't take into account for the z-axis. Do any of your models predict the terminal velocity? None of the models predict the terminal velocity since the maximum falling speed was not reached. An experiment that would be possible. To account for this, dropping an object from tall origin and seeing when the velocity stops increasing during the fall to find the max possible falling speed. Imagine the object were initially thrown straight up with same initial speed. Will this time be the same? It would take the same amount of time because the initial velocity is the same. Newton's second law shows that the initial force on the object is the same. Because of this, they will have the same change in momentum. Both the velocity update and position update equations show the position for the original will be greater while the max height for the new one will be greater.